In this lecture, we will derive the force on a current carrying conductor when it is placed in a magnetic field. So let us say that there is this conductor of uniform cross section S, and it is placed in a magnetic field B. Now we need to find the force on this conductor. Now, by experiments, it is seen that whenever a current carrying conductor is placed in a magnetic field, it experiences a force. Now, we need to derive the expression of that force. Now, since this is carrying a current, let us say this is carrying current I, and I will be current density into the surface area. I am assuming the current density is perpendicular to this cross section. That's why the dot product is simply JS here. So the charge carriers, if electrons are the charge carriers, they will be having an average drift velocity in this direction. So each electron will be experiencing a force given by Q V cross B. Now, if there are n electrons per unit volume, so a small volume will be having n delta V electrons in that volume. So the total charge will be n delta V into Q. So the force on this total volume, because since these electrons will be experiencing that force, and that force will then be transferred to that volume, will be n delta V Q, that is the total charge, and the average drift velocity of these all charges into B. Now, in our previous lecture, we have seen that this NQV is simply the current density J. So, force in a volume or per unit volume is given by J cross B, or F is equal to, on a total volume, J cross B into delta V. Now, for a conductor, for uniform cross section, I can write delta V as S into delta L, the length. Okay. Now, this is the force on this conductor. Now, this J S gives us the current. Assuming that this J is perpendicular to the cross sections or the cross section surface area of this conductor, then this Js is simply I. Now I will want to transfer the vector sign from J to the L, that is the length of this conductor, assuming that this delta L segment is a vector and it is in the direction of the current. So since this current density, then I can transfer this sign to here. So I can write Js delta L cross B is equal to the force on the conductor. Now this Js is the current delta L cross B. So on a small length of the wire, current carrying wire in a field, we get this force. So the total force will be IDL cross B when DL is varied from 0 to the total length of the conductor. So in this way, we can find the total force on the conductor. Now in this case, we have assumed that this current carrying conductor will also create its own field, but we are assuming that the field created by this current is so small compared to the already existing external field that we are just considering its effect only, and we are neglecting the effect of the self magnetic field. However, in the equation, the Lorentz force equation, the field is the total resultant field on at that point. We should remember that. So the force on a conductor placed in an external electric field is given as ideal cross B, or if I is and B are uniform, we can integrate over the full length, and it will give us this total force on the conductor. So in this way, we have derived the total force on a current carrying conductor in an external applied magnetic field. So if you find that this lecture is helpful to you, then please share and subscribe our YouTube channel, and also join our Telegram group whose link is given in the description of this video. Thank you.